A uniformly charged thin rod has length d and total charge capital Q. The rod is lying on the horizontal axis. First of all, we'd like to find the electric potential at point A, which is at a distance x from the right end of the rod, also on the horizontal axis. This is a one-dimensional problem. As always, let's imagine dividing the rod into small pieces, each of which will act like a particle, like a charged particle, and we'll find an expression for the electric potential created at point A by each of these particles. Here's such a piece that acts like a point particle. It has charge dq. Now, in order to find an expression for the electric potential that this particle creates at point A, we need to come up with an expression for the horizontal position of this particle, also for its width, basically. So now for the horizontal position variable, I'm using s instead of x because x is already defined as the distance between point A and the right end of the rod. So x is reserved for something else. So instead of x, which is the usually used variable for the horizontal position, instead of x we are using variable s. So then this particle dq is at a position s from the origin. The origin is the leftmost end of the rod, and it has width equal to ds, like so. Now let's remember the formula for electric potential created by a charged particle at a distance r. So here's the general formula for electric potential created by a particle of charge q at a distance r. Now, using the formula for the particle, we can come up with an expression for the electric potential created by unit charge element dq. It's basically the same thing, but the charge will be dq instead of q. And the distance between our unit element and A is basically x plus d minus s. So instead of r, we put x plus d minus s for the distance between the charge dq and point A. And this we call this dV. This is the electric potential created by the unit charge element at point A. And the total electric potential will be the integral of dV. Here we have set up our integral. Now this is all great, but we can't really integrate over dq, right? We need to express dq in terms of ds because s is our integration variable, right? Every unit charge element is at a different position s, so s changes, and that should be our integration variable. So next, let's come up with an expression for dq in terms of s and the given variables in this problem. In order to do this, let's use the idea of linear charge density. Linear charge density is defined as total charge divided by total length, and we use lambda to represent linear charge density. So lambda is equal to capital Q divided by d. Capital Q is the total charge of the rod, and d is the total length of the rod. Now, the unit charge element also has the same linear charge density. So we can also express lambda as dq divided by ds, dq being the charge of the unit charge element, and ds being the width of the unit charge element. So then capital Q divided by d is equal to dq divided by ds. If you combine the two, to eliminate lambda, it's a variable that we introduced and now we're eliminating it. We can find the connection between dq and ds, which is the actual integration variable, and the other given variables in the problem, capital Q and d. So if we rearrange our equation and isolate dq, we get dq equals capital Q times ds divided by d. Again, capital Q is the total charge on the rod, which is given. D is the length of the rod, that's also given. ds is our integration variable, that's the horizontal position variable. Now let's substitute this back into our integral. Here's what we get when we do that, and then we'll solve our integral. Now that we have our actual integration variable, let's also set our lower bound and the upper bound. S runs from 0 all the way to D, which is the total length of our rod. In the next line, I'm going to pull out all the constants and then take this integral. Here's our integral with all the constants pulled out of the integration sign. Now this is a fairly straightforward integral. If you want, you can use a u substitution. So you can set u equals x plus d minus s, the whole thing in the denominator. In that case, du becomes equal to negative ds. And the integral of this is natural logarithm, basically. So it'll be negative natural log of x plus d minus s. Here's the result of our integral with natural log. Also, we have an overall negative sign. In the last step, I got rid of that negative sign and I reversed the order of my integral limit. So instead of running from 0 to d, it runs from d to 0. In the next step, let's evaluate our integral. And here's our result, the result of our integral evaluated from s equals d to s equals 0. Now, this expression could be simplified further like so. Here's our final result for the electric potential created by the rod at point A. It's equal to capital Q divided by 4 pi epsilon 0 d times ln of x plus d divided by x. If x is much larger than d, or x goes to infinity, we can ignore the d next to x in the numerator. So the ln term reduces to ln of x divided by x, which is basically ln of 1, and that's equal to 0. So as x goes to infinity, in other words, as a point A goes really far from the rod, then the potential goes to 0 as expected, because potential at infinity is equal to 0. Next, let's calculate the electric potential at point B, and point B is at a vertical distance y from the right end of the rod. To find the total electric potential, again we're going to integrate over dV, dV being the electric potential due to unit charge element dq. Now, finding the distance between dq and point B is a little tricky. So if you think about it, focus on this triangle right here, this one, and the distance, the white segment, is the distance between dq and point B. Now, the two right legs of the triangle are y, the vertical one is y, and the horizontal one is d minus s, right? And the white segment, the actual distance that we're looking for, is the hypotenuse of this triangle. So then the distance we're looking for, the distance between point B and the unit charge element dq, is equal to square root of y squared plus d minus s squared. Substituting that in the expression for dV, this is what we get. The next step is again to express dq in terms of ds, which is going to be again our integration variable, since every unit charge element has a different position s. And it's basically the same thing. dq is going to be equal to capital Q divided by d times ds. Here's our integral with dq substituted as well. In the next step, let's pull all the constants outside of the integration sign. Also, let's put our lower and upper bounds and also use a u substitution. Capital Q divided by 4 pi epsilon 0 d, that's a constant. We pull it outside of the integration sign. Now, s runs from 0 to d. Those are our integral bounds. And we use the u substitution, u equals d minus s. So let's rewrite our integral. Here's our integral after the u substitution. Now this one is not a straightforward integral, so we use an integral table to solve this one. Here's our final result. As y goes to infinity, we can ignore the d in the numerator. So we have d here and then another d squared here. We can ignore those. We can set these equal to 0 because they're being added to y squared or y, right? So if we ignore those, we get in parentheses, we get y divided by y, which is equal to 1. And again, ln of 1 is equal to 0. So potential goes to 0 as y goes to infinity. In other words, if point B is really far from the rod, the potential at point B becomes equal to 0 as expected.